To understand extreme heat, we start with the core of our sun. This gravitational engine maintains a temperature of approximately 10 million degrees Celsius. While 10 million degrees is the natural benchmark for our solar system, human experiments have since surpassed this temperature by several orders of magnitude. Reaching these levels required physics so volatile that early researchers had to calculate whether a single experiment might accidentally ignite the Earth's atmosphere. This pursuit was fueled by the mid-century struggle for global dominance, where generating extreme heat became a primary measure of a nation's technological power. This arms race turned thermal output into a quantifiable weapon, forcing us to engineer conditions that don't exist anywhere else in nature. The journey to these extremes began in 1945 with the Trinity nuclear test in New Mexico. It was the first time we attempted to replicate the internal conditions of a star on the ground. At the moment of detonation, a massive fireball formed briefly overrode the natural physical laws of our atmosphere. The explosion generated 15 million degrees Celsius. For the first time, human engineering had produced an environment hotter than the center of the sun. The intensity was high enough to flash melt the desert sand into these green glass fragments, a material now known as trinitite. By 1961, the Soviet Union responded with the Tsar Bomba, pushing the limits of nuclear thermal output even further. This test reached 100 million degrees Celsius, exactly 7 times hotter than the core of the sun. This massive jump in temperature was possible because the design moved from fission, which splits atoms, to fusion, which crushes them together. By the early 1960s, these tests had reached a scale where further atmospheric increases would have risked massive environmental contamination, ending the era of surface-level thermal records. In 2012, the focus of high-temperature physics shifted. The goal was no longer destruction, but the discovery of subatomic particles. To reach the next thermal peak, researchers moved deep underground into the Large Hadron Collider in Switzerland. The process involves accelerating particles to near the speed of light before forcing them into a head-on collision. Unlike a bomb, this creates a point of heat that is trillions of degrees in intensity, but only microscopic in size. A moment of wonder. The 2012 experiments achieved a staggering 5.5 trillion degrees Celsius. This screen shows the digital evidence of a collision. Physicists use these data visualizations at the CMS experiment to track and verify these trillion-degree events. This achievement demonstrated that observing the earliest states of the universe requires temperatures that dwarf those found in the centers of stars. This chart shows the disparity between the two records. CERN's peak is 360,000 times hotter than the center of the sun. At 5.5 trillion degrees, matter dissolves into a prehistoric state known as quark-gluon plasma, where particles like protons and neutrons cannot exist. The entire universe was in this exact physical state just fractions of a second after the Big Bang. For the brief moments these particles collide, the hottest known environment in the universe is located inside a tunnel beneath Switzerland. Our ability to harness these temperatures to study the origin of matter stands as a testament to the reach of human curiosity.